Okay, so the first problem which we are going to discuss is find the complement of a function f equal to x bar y z bar plus x bar y bar z. So before getting on the problem, let us just see what exactly a complement is. So let's consider a variable x, and let's assume that it has two possibilities, that is 0 and 1. Now, the complement of x bar is nothing but reverse operation. That is, if it is 0, it becomes 1. If it is 1, it becomes 0. In logic gates, it's called the NOR gate. So, NOT gate, here it becomes, and it is here 0 becomes 1 and 1 becomes 0, and it is represented using this representation, that is a triangle, on top of it a circle, a small circle. So here x, if you are giving x as input, you get the output as x bar. So there are two ways to represent the complement. Either you can represent it as x dash, or you can represent it as x bar. So this is about the complement. Now let us see our question. It says f is a function which is given as x bar y and z bar plus x bar y bar and z. So this is our given question. We need to find the complement of the whole function. Now the solution. Let's write down the given expression, that is x bar y z bar plus x bar y bar and z. The whole complement. This is what we need to find. Now there is a law called the De Morgan's law, which states that now if there are two variables a plus b, to find the whole complement of these two variables, we do, that is a plus b, the whole complement is nothing but complement of the first variable into, that is dot, complement of the second variable. This is called the De Morgan's law. De Morgan's law, which states that for two variables, a plus b whole complement equal to a complement into b complement. Just remember, if there is plus here, it becomes into here. Now, similarly, we have one more law, one more condition. A into b, the whole complement becomes a complement plus b complement. So just an easy way to remember, if there is plus here, it becomes a dot operator here. If there is a dot operator here, then it becomes a plus operator here. And complement of both variables. So this is De Morgan's law for two variables. Similarly, we have De Morgan's law for three variables. That is A plus B plus C. The whole complement will become complement of the individual variables, and the plus will be replaced by dot operator. That is, it becomes A complement into B complement into C complement. Okay, let me represent this much darker. So A plus B plus C, the whole complement, becomes A complement dot B complement dot C complement. Similarly, A dot B dot C whole complement becomes A complement plus B complement plus C complement. These are called the De Morgan's law for two variables and three variables respectively. Simple way to remember: two variables given and we need to find the whole complement. We need to take the complement of the first digit, second digit, and if there is plus here, it becomes dot, and if there is dot, it becomes plus. Simple way. Now, coming back to our question. We have x complement y z complement plus x complement y complement z. Let us consider this as two separate things. Let this be A and let this be B. Now, if we can simplify this, it is nothing but A plus B, the whole complement. So what is A plus B whole complement? We just saw. That is A complement into B complement. So we can write this as x, y, z bar, x complement, y, z complement, dot x complement, y complement, and z. Whole complement of both the things. Because A complement plus B complement is equal to, A plus B whole complement is equal to A complement dot B complement. Okay. Now, here we have two separate functions. Now, let us see the first bracket, that is x complement y z complement. We know that from De Morgan's law, A into B into C equals, A into B into C whole complement equals A complement plus B complement plus C complement. Using that here, we get x complement, the whole complement, plus y complement, plus z complement, the whole complement. This bracket can be simplified this way. And now into, applying the similar rule here, we have x complement, the whole complement, plus y complement, the whole complement, plus z complement. Now simplifying further, we will have x complement, the whole complement is nothing but x. Now y complement plus z complement, the whole complement is z, dot. Here x complement, the whole complement is x, plus y complement, the whole complement is y, and now here z complement is z. So this is the simplified expression of the given function. That is, complement of this function results this. Now, the rule that we used here is now a dot b dot whole complement equals a complement plus b complement plus c complement. So, such type of problem can be solved using the De Morgan's laws. Now, going to the next problem. Design the logic circuit for half adder. Now, before designing logical circuit for a half adder, we need to know what a half adder is. So a half adder is a combinational circuit that takes two inputs x and y and produces two outputs called sum and carry. So this is how a half adder is represented. HA means half adder. So here we give two inputs, that is x and y, and we get two outputs called sum and carry. Now we can design a truth table for this. These two represent the inputs, and here sum and carry will represent the outputs. So x and y. So we have inputs as 0, 0, 0, 1, 1, 0, and 1, 1. Okay. For these inputs, sum is nothing but addition. So 0 plus 0 will give us the sum 0. Since no carry is produced, the carry will be 0. Similarly, 0 plus 1, the sum is 1 and the carry is 0. No carry is produced. Similarly, 1, 0, sum is 1, carry is 0. Now, 1 plus 1, sum is 1, carry is also, sum is 0 and carry is 1. What we have done here is simple binary addition. Now, for this, we need to design a logical circuit. Now, sum can be represented as, since we have one at two terms, that is x bar y plus x y bar, and the carry we have only uh, one expression which gives the output as 1, that is x1. Now let us write it down. Sum, what did we get? X bar y plus x y bar, and the carry is x5. So we need to design a logic circuit for these two. So let us see for sum. So here we have two inputs, x, y. This expression is nothing but the XOR gate representation of two variables, x complement y plus xy complement. So using the XOR gate, we can represent these two x, y using the XOR gate. We get the sum. Now here carry. For carry, we have an AND operator, that is x, y. We get c. So these two are the logic gates. We can represent it. We can represent the logic gates separately or in a single, uh, into a single format also. That is combining both the expressions together. We have x and y. So x and y. Let us take these two expressions. Now x bar y plus xy bar is nothing but the XOR gate. Those two can be represented here this way. And now x and y. X dot y can be represented here for the carry in this way. That is here. So this is the sum and this is the carry. So we have two inputs. We have got two outputs, sum and carry. So this is the required logical circuit. The logic circuit for half adder can be represented either this way or this way.
Okay. The section B, the first question. Perform the following operations on given numbers. So in the first A bit, we have to perform given operations. In the first A question, first bit, we are asking to do addition for two binary numbers. The two binary numbers given are 11001 and 10001. So we have to perform binary addition. In binary addition, the rules are simple. If you have if you have two zeros, then the sum will be zero and there will be no carry. So we are adding 0 and 1. And the sum will be 1 and will have no carry. If we are adding two ones, then we'll have sum 0 and we have to take 1 carry. 1 as carry. If we are adding three ones, that is the carry from the previous one, and two ones, then we'll have the sum as 1 and 1 carry. So using the same rules here, we can add these two given binary numbers. So we have 1 plus 1. The sum is 1. We'll take 1 carry. Now 1 plus 0 is nothing but 1. 0 plus 0, nothing but 0. 1 plus 0, 1. 1 plus 1, the sum is 0 and we have a carry 1. So that carry comes down 1. So this is the answer of the binary, the answer we get when we add these two binary numbers. Answer is 1 0 1 0 1 0. Let us go to the next bit. In the next bit, he is asking to subtract two binary numbers using two's complement. The two binary numbers are triple one double zero minus 10100. Using two's complement, we have to perform this binary subtraction. Two's complement method, we have to perform this binary subtraction. In the two's complement method, the second number we have is we consider it as a negative number. That is, we consider the above binary, the above operation we have as triple one double zero plus minus of 10100. So this is a negative binary number. To represent it in a normal binary form, we use using the two's complement method. We have to take, that is, to represent it in two's complement method, we have to take its ones complement and add 1 to it. So ones complement of this number we have will be nothing but we have to take zeros in the place of ones and ones in the place of zeros. So the ones complement of the following number will be nothing but 0, 1, 0, 1, 1. Let us take an extra bit here in this number 0 finally, so that when we take one's complement finally we get 1, because in all negative numbers the most significant bit is 1. So this is the ones complement of the given number 10100. Now we have to add 1 to it to get the two's complement of the number. So adding 1. Now we have to perform normal binary addition. 1 plus 1, we have 0, carry 1. 1 plus 1, we have 0, carry 1. 1 plus 0, 1. 1 as it is, 0 as it is, and 1 as it is. This is the two's complement of the given number 10100. Here we are finally getting 1 in the most significant bit place, representing it is a negative number. Now we will add this number to our already existing number triple one double zero. Then we will get our needed answer. Let's add those two numbers. Triple one zero plus zero zero one one zero one. Now we have to perform normal binary addition. As we have seen the rules here, we can use this, apply these rules, and we have to perform addition. 0 plus 0, answer is 0. 0 plus 0, it is 0. 1 plus 1, 0, and we get another carry 1. 1 plus 1 plus 1, adding 3 ones, we get sum 1 and carry 1. So we take sum 1 and carry 1. 1 plus 1, sum 0, carry 1. 1 plus 1, Again sum 0, carry 1. Carry 1, I will write down. This will be our answer. But when we are performing subtraction using 2's complement method, in the final result, we will ignore the not significant bit. So this bit is ignored. This one is ignored. So our answer to the question triple one zero minus 10100 will be, we have ignored one here, so our answer will be 0 0 1 0. This is our answer.